We now look at the weight of a person in the space station in orbit, of a person in orbit. Now, normally we say that the people are weightless, and if you have the spaceship or the space station or a satellite and the people inside, they're floating around and they can just move around there, and so they're weightless. But let's see if they really are weightless. So the weight is mg. So what we want to find is that here's the surface of the Earth, and here's this satellite moving over the Earth at a distance h above the surface. We add the radius of the Earth to it. So what is the value of g over here at this distance? And for that, we would use g equals g, mass of the Earth, over the radius of the Earth plus the height. Now, considering the space station, which is at an average height of 350 kilometers above the surface of the Earth, and the radius of the Earth itself is RE is 6371, and this is 350, so it becomes 6271 kilometers. So if we plug in these numbers, the value of g, 6.674 into 10 to the power minus 11, the mass of the Earth, 5.97 into 10 to the power 24, and 6.721 into 10 to the power 3, and convert to meters becomes 6, and square. This gives us a value of 8.82 meters per second square. So if the person had a mass of, for example, 100 kilograms, then the weight of the person would be 882 newtons when he's in the space station. Now, on the surface of the Earth, this person would have a mass of a weight of 100 times 9.8, which is 980 newtons. So he's pretty heavy still in the space station. But we say that the person is weightless. How then can he float around? Why doesn't he stand on the surface? Because he's pretty heavy. And the reason is that as the space station is moving around in a circular, or let's assume a circular orbit, it's actually continuously falling down. So let's consider this case of a tall building, and you have an elevator in that tall building, and you have a weighing machine on the floor, and a person is standing on that weighing machine, and he gets his weight. And then there's a cable up here, and you cut the cable and let this fall down, free fall. So as it's falling down with an acceleration of 9.8 meters per second square, the person inside will no longer be standing on the machine, but he'll just be floating around. And the machine would not be on the floor either. Everything is falling down with the same rate, and the person in here would be weightless, even though the value of g is still 9.8, and so his weight is still mg, but he's weightless inside this thing. So it's like even that in free fall, the person feels a state of weightlessness, because he cannot, if he attaches himself to a spring balance, he show a weight of 0, because the spring balance itself is falling down along with him. So relatively, he's just weightless. And for the case of the space station or a satellite in orbit, when it's going around in a circular orbit, it's like it should be going straight, but it doesn't. So it's like going and falling down. So it's going and falling down. So it's in a continuous state of falling down towards the Earth with an acceleration which is AC, which is g. That's the centripetal acceleration. So because it's continuously falling down, it's just like a person falling down here, and during that time the person is weightless. Now if you want to try it out, go to one of those amusement rides where they take people very high up, and then the whole thing falls down for a certain distance, and they have to slow it down. But while it's falling down, if you're sitting in one of those seats and you hold something in your hand while you're falling down, that object, suppose it was heavy, will no longer have to hold it up because it's falling down along with you and it's weightless. Okay, so now we look at the last topic in this portion, and that is the escape velocity. So if this is the surface of the Earth and you throw an object vertically up, it's going to go up, slow down, and fall down. So you throw it with a bigger velocity, so it goes higher, and as it's going up, it gets slower and slower and slower until it reaches a speed of 0, and then it starts falling down again, and then it comes down. So you throw it with a bigger velocity, and it goes higher, and then it falls down. So is there a speed with which you throw it so that it goes up, 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 and never returns? And that would be the case where the velocity is so much that it goes down and slows to 0 at a distance that's infinite. So it slows down to 0 at an infinite distance, and then it's going to fall down. Of course, it's not going to reach there, so it's not going to fall down. And that speed with which, if you throw it, it never returns, is called the escape velocity or the escape speed. And the escape speed is given by 2g mass of for the Earth. It's 2g mass of the Earth over the radius of the Earth, square root. So by plugging in the numbers, we get a value for Earth as 11.2 kilometers per second. So if something leaves off at that speed, it's never going to return. Now, for the moon, the mass of the moon is smaller and the radius is also smaller. When you plug in the numbers, the escape velocity for the moon is 2.3 kilometers per second. So if you from the moon, it's much easier to throw something up that falls to that would never return. And because the Earth is so much bigger and heavier, so when we take a satellite from the Earth to the moon, we need a rocket that's a Saturn V rocket, and it's big and heavy. It goes to the moon, and there's a little spacecraft that sits there. When it wants to come back, it doesn't need a Saturn V rocket. It takes this little top portion with it, and this little thing is enough to bring it back to the Earth. If we go to a planet that is of comparable size to the Earth, such as Venus, well, to go back from Venus to Earth, we would need a Saturn V rocket, which means we have to take that rocket with us. And so this would have to be still much bigger because it's carrying a rocket of its own size. So it's going to require some really new technology to be able to go to a heavier planet. Well, heavier than Earth would be really difficult, but even a planet of similar size, we can go there, but to return you need a Saturn V rocket.